Conversations.
Yeah, your conversations.
Yeah.
Hey, Jasmine, I'll take your quiz.
So it means five. So it's two. What does it mean? Making the addition problems into multiplication problems. Or was that something else?
It's part of it. But I don't know if it's like. You can do that.
Right.
Yeah, I know that's it. Let's see.
Okay, well, that already sounds pretty quiet in here, so let's go ahead and get started. What does it mean to factor a polynomial? What are we doing? Chris, you were about to say something?
No.
No, okay. Matthew?
We're turning polynomials into multiplication.
We are. We're turning a polynomial, which is fundamentally an addition problem, and we're turning that addition problem into a multiplication problem. And this is what we've been talking about and focusing on for many class periods now, and it is at the heart of a very creative problem-solving strategy that was invented hundreds of years ago by some mathematicians who wanted to be able to solve polynomial problems. So now that we've been practicing turning addition into multiplication for so long, today we get to start applying that to solve the types of problems that they were trying to solve hundreds of years ago. And this shift, translating from adding to multiplication, was the shift they needed in order to allow new types of problems to be solved that they previously could not solve. So that's the main idea. We've been translating addition into multiplication. Okay, so the first game. I'm thinking of two numbers that add to 10. Which two numbers am I thinking of? Let's just get us started.
5 and 5.
5 and 5, that was not my number. That was not it, but it was a nice guess. A plus B equals 10. It was not 5 and 5. Another guess? Jackie? Any two numbers that add to 10?
10 and 0.
Oh, 10 and 0. Good guess. That was not it. Ingrid?
8 and 2.
8 and 2? No, that was not my numbers. Now, what do you think, folks? If just enough of you guess, will you eventually get it?
Yeah.
Oh, okay. Well, keep going. What was it?
9
What's
and
another
1.
guess? Martha? 9 and 1? No. Another guess?
6 and 4.
6 and 4? No. 7 and 3? No. Is that it?
11 and negative 1.
11 and negative 1? Very good. No, that was not it either. Another guess? 100 and negative 90? That's fun. No, that was not it, but a nice guess. What other numbers add to make 10?
Negative 10 and 0.
Negative 10 and 0? Does that add to make 10? No, that was negative 10. No, nice guess, though. You could have done
Negative 0.
Negative 0? Maybe it could have been negative 10 and 20. That would have worked. Yeah, those add up to 10. What about 10.1 and negative 0.1? Do those add up to 10 as well? Yeah. What about 10 and a fourth and negative a fourth?
Oh,
Now up to 10 too. Did you guys have any prayer of getting this?
No.
Not a prayer. You did not have a prayer of guessing my two numbers that added to 10. You were never going to get it.
So we still do $100.
Well, at some point, no, you have to win the game to do it. But nobody even won a penny that time. My goodness. Okay, so what were my two numbers that I was thinking of? I was just thinking of 3.5 and 6.5.
Oh.
Okay, well, let's try a different game now, okay? New game, new winners. So I'm thinking of two numbers that add to equal 0. What are my numbers? So just go ahead and take a guess there, Deegan. What numbers add to 0 that I'm thinking of?
To add to 0.
Yeah, that add to 0.
0.5 and negative 0.5.
Okay, good. 0.5 and negative 0.5. Those weren't my two numbers, but those were two good numbers. Jesus?
0 and 0.
Well, good guess. 0 and 0. Had I been thinking, that would have been my second choice, Jesus. That was really close. What? Wait, what? You don't even get a penny. Sorry. Another guess? What adds to 0? Let's see. Stephanie? Two more numbers that add to 0? Any two numbers. I'll come back to you, Don.
Negative 4.
Yeah, negative 4 and 4. Another two numbers. Jasmine? Negative 3 and 3. These are all good guesses. What do you notice now about your guesses? I mean, they have to be the same number, right?
Yeah.
But one's plus and one minus. So we know a little more, don't we? In this game, it could have been anything in the whole wide universe. Whereas in this game, we've narrowed it down a little bit, even though you still don't know what number I'm guessing. If someone had guessed x and negative x, you'd have been really close, right? Because that does capture what my two numbers are. My numbers would have been one number positive and one number negative. Okay, well, nobody guessed my number. I was guessing 17 and negative 17. So no pennies for anyone.
I was half.
What?
-7 and 7.
Oh, is that what you were going to guess? Oh, so close. -7 and 7. Yep, those add to 0. Okay, let's try another game. I'm thinking of two numbers that multiply to make 10. Again, you can win a penny or $100. You just have to guess my two numbers that multiply to make 10.
I have a question.
Yeah, Dick.
Can we specify the range?
The range?
So we can know where to start?
No, you just have to guess. Yeah. So what two numbers am I thinking of that multiply to make 10?
2 and 5.
It could be 2 and 5. That wasn't my numbers. What else? And what, Genesis?
I said obviously those are not your numbers. You're
Yeah.
kind of-
Yeah, I would have never chosen those. Now when $100 is on the line. What are some more? It could have been 10 and what? What?
We had another moment.
They multiply to make 10. Yeah. So 10 and 1, or there's still lots and lots of other options, right?
0.5 and 20.
Yeah, it could be 0.5 and 20. What else? It could be negative 0.5 and negative 20, right? Because a negative times a negative is positive, so it could be that. It could be 1/10 and what, 20? Oh, well, that's kind of the same thing. Wait a minute, that's half. No, 200. Is that correct? No, 100. There we go. Yeah, 1/10 and 100, that would multiply to make 10. Any other guesses about what numbers multiply to make 10?
Negative 0.25 and 40.
Yeah, good. Negative 0.25 and 40. I really like that guess. It wasn't what I was thinking, but really close. I mean, it's a good guess because those two numbers do in fact. Wait, did you say negative 40?
Yeah.
Yeah.
Why
So
did I say that?
they also multiply to make 10. Negative 10 and negative 1. Yep, that's another good guess. Okay. So far, no one has guessed any of the numbers I was thinking of, but I certainly wanted to demonstrate the diversity of possible guesses, right? Did you ever have a prayer of guessing my two numbers?
Yeah.
No, you didn't. You had no prayer. How many different numbers could multiply to equal 10? How many a lot? How many different numbers would multiply to equal 10?
Probably 20.
Infinitely many. There were infinitely many. You had no chance of winning a penny. You had no chance of winning $100 at all. Okay, so my first three games were really stacked against you, folks. Really stacked against you. So now my last game,
What were your
I'm
numbers?
thinking, what?
Your numbers.
Oh, what were my numbers that time? Oh, my numbers that time were 30 and a third.
No.
Yeah, 30 and a third. Okay, so now what? I'm thinking of two numbers and they multiply to equal 0. Jesus, you want to go first? And? Oh man, you guessed one of my numbers. One of my numbers was 0, not the 3,875. So Jesus gets a penny. Anyone else want to try to guess my numbers? Stephanie, what do you think? What two numbers multiply to equal 0? Ooh, negative 0 times 0. That is another really good guess. That wasn't my number, but you did guess one of my numbers, so you also get a penny. One of my numbers was 0. Anyone else want to take a guess? Mick, what do you think? What are my two numbers?
I'm not gonna win anything.
You could win at least a
I
penny.
don't want a penny.
You don't want a penny. Oh man, this is rough. Okay, Kim, you got a guess? Oh good, 25 and 0. Not 25, but the 0 is correct. You also get a penny. Manuel?
0 times 0.
0 times 0. Well, that's very similar to, was that you, Stephanie? You said? Yeah, very similar. You get one of the numbers correct.
Because it's the same number for both. So
Well, but I said I'm thinking of two numbers. Yeah, you got one of my numbers. Yeah, I see what you're doing there, Manuel. That was a good try. Yes, Manuel gets a penny as well. The actual numbers I was thinking of, what?
15 0?
15 0? No, I wasn't thinking of 15 0. But you get a penny as well. I was thinking of 111 times 0. Yeah, you're really close. So, folks, did you ever have a prayer of getting $100?
No.
Did you ever really have a prayer of getting $100? How many different numbers add to 10? Infinitely many pairs of numbers add to 10. How many pairs of numbers add to 0? Infinitely many pairs of numbers add to 0. How many pairs of numbers multiply to make 10? Infinitely many numbers multiply to make 10. And how many different pairs of numbers multiply to make 0? Well, a lot, but you know one of them, right? What does one of those numbers have to be?
0.
0. So the best that you guys were ever going to do was win a penny from me on this game situation, because your chance of guessing this was 0. Your chance of guessing this was 1 out of infinity. That's 0. Your guess of chancing that was 1 out of infinity. That's 0. But your chance of guessing one of my numbers was guaranteed. Your chance of guessing one of my numbers here was guaranteed, right? Because you knew that one of the numbers had to be 0. And believe it or not, that's the fundamental shift that mathematicians needed back in the, say, 1500s, 1400s, around then, to actually start solving some really good problems that previous to then, they were not able to solve. Okay, so let's get started. I have pennies in my pocket, so for all of you who want a penny, I'll give it to you after class. So here we are. Today is what, February 14th? Happy anniversary, Arizona. Happy Valentine's Day. We're ahead of schedule, so we're just going to keep on moving on with where we are, which is, I think, 6-6 or 6-7. Your test is a whole week away from now. You don't have school on Monday, and then we'll have 2 more class periods and then your test. And I have a new joke for you today. Why is the math book always unhappy? Yes, it has so many problems.
What's the other one?
What's the other what? Oh, what did the Buddhist say, or what did the Buddhist ask the hot dog vendor? Make me one with everything. Kristen was absent. She didn't hear that joke. All right, so here we go, folks. Review what we've done. We've come a long way. If you notice, I grouped these. I grouped these together a little bit. How did I group them? These are all the different factoring techniques we've looked at so far, all the different ways that we can translate addition into multiplication. Why did I group these first 2 together? Say that again? Yeah, I'm just taking something out, right? I either took out a 2 or a -1, but it's really just a single number. It's nothing very exciting. It's not rewriting it as a product of binomials, so it's really not that exciting. But you have to look for that. You have to look to see if you can factor out a number, or look to see if you can factor out a negative. Why did I group these 2 together? What, Deacon?
Turn it into a multiplication problem.
Yeah, that's true, because this, basic factoring, this is kind of like our core strategy. What do you multiply to get this number that adds to get this number? And then non-basic factoring is what you do if the first number is not 1x squared, right? If it's 1x squared, you can do basic factoring. If it's a something x squared, like 5x squared, you have to do a different technique. But this is still like the bread and butter of what we do. This is the core strategy of factoring. Why did I group these 2 together? Anyone want to take a guess?
Most of those numbers can be squared.
Well, that's true. Both of these have square numbers in them, right? This is a difference of squares, so those are both squares. And this last number here is always going to be a square number, isn't it? Isn't that last number always going to be a square number? If I square a binomial, the last term is always going to be a square. And these are just 2 special cases. They're very special cases. I mean, what are the odds that someone's going to walk up to you and hand you a difference of square or a perfect square binomial? They're rare. It's not going to happen all the time. You're much more likely to get a problem like these. But these are just special cases, right? They're special cases of rules that you might want to be familiar with. And then finally, factoring by grouping. It's just, I left that one by itself because it's just kind of its own thing, where you group these first 2 together and you group those last 2 together. Okay, so did we already talk about you making a list of these and having them handy and nearby, so when you're doing your homework on my math lab, or you're just working on homework? So you'd want to have all those strategies written on a list so that you can always kind of look at them and consult them. Nick?
I have a question. So all the tests, can we use our factor thing or no? Like
No.
table?
No, I'm glad that you'd like to use it. It's very convenient. But before the test, if I haven't already shown you yet, I'll show you how to use your calculator to make a factor table. In fact, what's your calculator?
Casio.
Oh, it's Casio. I don't know how to do it on the Casio. We can look at it together, but you basically just sit there and divide by every counting number. It'll make a factor table for you. All right, so this would be a good thing to have, a good tool. So here we go. We're beginning section 6.7. In section 6.7, we're introduced to the idea called the zero product rule. The zero product rule. This phrase, the zero product rule, states that if you have 2 numbers, A and B, multiplying to equal 0, so sorry, I should have said if A times B equals 0, then what? what do you know? If A times B equals 0, then what do we know for sure? One of them is 0. So then A equals 0, or B equals 0, or both are equal to 0. Right, but we know it has to be one or the other. This is the fundamental technique that kind of exploded mathematics in, say, the 1500s, 1600s, because they were able to solve polynomial problems. So, taking a look at this first problem, we have a polynomial that has already been factored. Right? This was already factored for you. What was the original problem? Using the sum product rule in your head? X squared, what? Negative 6 plus 4 minus 2x? And negative 6 times 4 minus 24? So you have to imagine this was the original problem. Right? This was the original problem that they were trying to solve. But then they factored it into this. So now they had x minus 6 times x plus 4 equals 0. And so right now I have something times something equals 0. What does that tell me about one of those? One of them had better be 0. And in fact, because x can take on any value in the universe, you know, I can plug in 1, I can plug in 10, I can plug in negative 20, I could make either of these equal to 0, right? If I choose the right value for x, I could make this one equal to 0. And if I choose the right value for x, I could make that one equal to 0. So everybody start right there with me. Draw two little arrows. Your two little arrows are showing you your alternate realities. You're saying, well, hey, one of them has to be 0. And in fact, depending on what I plug in for x, I could make both of them equal to 0. Not simultaneously, but I can choose to make either of them 0. And so at this point, you just solve for x. X minus 6 is equal to 0. You add your 6 over. And one possibility is x equals 6. The other possibility, subtracting your 4 over, is x equals negative 4. Those are the two numbers that you could plug in to make that equation equal to 0. And let's look at it concretely. I'm going to take this equation. I'm going to write it again. That's x minus 6, x plus 4 equals 0. And first, I'm going to let x equal 6. What happens if I let x equal 6? Like, plug it in into both places. Here, 6 minus 6 is 0. And here, 6 plus 4 is 10. But is 0 times 10 equal to 0? Yeah, so it worked out. You notice I wasn't trying to make both of them equal to 0. All I have to do is make one of them equal to 0, and that will make the whole product equal to 0. What about if I let x equal negative 4? Then I have negative 4 minus 6 is negative 10, and negative 4 plus 4 is 0. And sure enough, negative 10 times 0 is equal to 0. Yeah, Jesse? Do I want you to do one instead of both?
Yeah, you said, one of them. So, all 50 you want to solve.
Oh, both. Yeah, you solve both. Yeah, you have to. You solve both because there are, in fact, two possibilities. If I want this equation to equal 0, there are actually two possible values I can plug in. Okay, so what if you let x equal anything else? Like, what's just a totally different value for x that we could try? 7. If I let x equal 7, then that 7 minus 6 is 1, times 7 plus 4 is 11, and 1 times 11 is not equal to 0. 1 times 11 is equal to 11, and 11 does not equal 0. So 7 was not the solution. Okay, this problem right here gives us a really nice overview of all the philosophy we've been talking about. Why do we say x equals 6 is the answer? Because what can you do with the 6? You plug it in, and it makes it true. You get 0 equals 0. So 6 is the solution because when you plug it in, it makes the equation true. Why is 7 not the solution? Because when you plug it in, you get a false statement. So 7 is not the solution. So what are the two solutions to this problem?
6 and
Yeah, we would just write down x equals 6 comma negative 4. There are two solutions to that equation. There are two numbers in the whole universe that would make x squared minus 2x minus 24 equal to 0. Remember, that's the original problem. That would have been the original problem mathematicians were dealing with in the 1400s, 1500s. And they wanted to find what value of x would make that thing equal to 0. And we just did it. We found the two values of x that would make that equation equal to 0. Keep in mind over here, folks, this is not a coordinate. Don't write down parentheses 6 comma negative 4 because that's a coordinate, and this we're not talking about a coordinate. We're just listing out the x values. It's just a list. Okay, question?
So basically, we're just taking the opposite of each number. Like, so, say for instance, you have -6, you have +6. negative
Yeah, Deegan makes a really good point. So we're basically just taking the opposite of each number. Is that a fair assessment?
Yeah.
That whatever number is inside the binomial is the opposite of that is going to be the solution? That's a fair assessment for now. If the binomial were 2x minus 4,
Then no, you can't.
then you'd have to write it out and actually solve it equal to 0, because then in that case, you're dividing off a number on the 2 and you get x equals 2. You're still taking the opposite sign, but you have to actually solve it. So yeah, as a shortcut, you are taking the opposite of that number. But the key is answering why. Why are you taking the opposite of that number? Why is it that you take the opposite of -6? Because what are you doing with the -6?
Moving it over.
You're taking it away from.
Then you're moving it to the other side of the equation, which is why the sign changes. Yeah. Okay. Well, very nice, folks. That's a nice little example of the zero product rule. Let's try that again. I'm just going to move that up so we can see this. Here we have a problem statement. What was the original problem? The original problem was x squared minus 0.1x minus 0.42. That was the original problem. And somebody was asking themselves, gee, what number can I plug in for x to make that thing equal 0? I'd really like to know. And so they factored it, and since this times this equals 0, I know that one or both, actually both, can be made to equal 0. I can force x minus 0.6 to equal 0 just by choosing to let x equal 0.6. If I choose to let x equal 0.6, I just forced this binomial to equal 0, and then 0 times anything will equal 0, and it will be true. Likewise, over here, I drop down my x plus 0.7 equals 0. I can force that to become 0 by letting x be x equals negative 0.7. So that would be the answer. You'd come over here and say, well, the two numbers in the universe that you can plug in to make that equation true are 0.6 and negative 0.7. Those are the only two numbers. Now, first of all, folks, do you believe it? Like, look back at the original polynomial that they factored to become this factorization. If you plug in 0.6 into that, will it really equal 0? Do you believe it? Should we try? Should we verify? Jasmine? You what?
I wrote the.
Okay.
I wrote +7, but I wrote it down wrong.
Okay, so you figured it out. Well, let's find out. If I plug in 0.6, I'm going to plug it into this polynomial. 0.6 squared minus 0.1 times 6 minus 0.42. Oh, I did something wrong. What's 0.6 times 0.7? Oh, it is 0.42. Oh, that's a plus. Sorry, folks. That's a plus right there. There we go. Okay, that equation. This is the equation that can be factored like so. And if I actually do 0.6 squared plus 0.1 times 0.6 minus 0.42, it really is 0. Okay, so it really does work. Obviously, you should do that on your own calculator to verify it for yourself. But the point is this strategy works. Let's try another one. Right down there. Is this still the same page for you?
No.
Okay, so you have some problem. And notice they already factored it for you. What was the original problem? Oh, I don't even want to foil that back together again. But can you imagine foiling it back together again and you'd get some answer? So we factored it. We have this. We say this times this equals 0. Therefore, I can force this to equal 0 if I want to. And I can force this to equal 0 if I want to. By simply letting x equal negative 1/4 or x equal 3/5. That will make the original equation true. Now you might be sitting there saying, so you're saying once I factor it, I just have to draw two little arrows, solve those equations, and I'm done? I think that's true. That's totally it. Once you're factored, you just draw those two little arrows, solve both of those equations, set equal to 0, and then you're done. That is the solution. And Deegan, here's a good one for your question. You were saying, can you just take the opposite of 11 and the opposite of 5? And the answer in this case is,
No, you still have to try it.
yeah, you definitely have to take these and solve each of them independently. Because if you just take the opposite of 11, that wouldn't be the right answer. So again, philosophically, we're saying this thing times this thing equals 0. And if that's to be true, if this times this will equal 0, then either 3y plus 11 has to equal 0, or 7y plus 5 has to equal 0. Either of those will work. Either of those solutions would work to make the original equation true. Now, folks, right here, I bet a lot of you could do that in your head. Who'd like to try? Y equals,
-3 or -2.6.
well, that's a decimal. I don't know.
Or 11/3.
Yeah, -11/3. You can probably do that in your head, a lot of you, because you move the 11 over, so that's -11, and then you divide by 3, so it's -11/3. I'm sure a lot of you can do it in your head. I would really like to see you do the work. Even if you at least write 3y equals -11, and then y equals -11/3. I really hesitate to say it's okay to just write down y equals -11/3. I think you should show your work, because otherwise I think we're going to make mistakes. So likewise here, even though you might just look at that and say, oh sure, y equals -5/7. I think you should at least write down your work that 7y equals -5, and then y equals -5/7. Remember, this is for your audience and your own brain. Okay, so folks, are those the correct solutions? Is y really equal to -11/3 and -5/7? Do both of those numbers, if you plug them in, does it really make it equal to 0? I'd like you to convince yourself. Everybody choose one of those to plug in and see if it really equals 0. So use your calculator. You can either do 3y plus 11 and plug in -11/3, or you can do 7y plus 5 and plug in -5/7. This is a good calculator skill for all of you. You should definitely know how to plug fractions into your calculator to verify these solutions. So for instance, your calculator will look like 3 parenthesis -11 divided by 3 parenthesis plus 11. That's what your calculator readout should say. Or if you're doing the other one, 7 parenthesis -5 divided by 7 parenthesis plus 5. So everyone choose one of those to do. I mean, what the heck, you could do both. But the key is to verify for yourself that these numbers that we just solved for really are making those binomials equal to 0. And if you make one of those binomials equal to 0, the whole product is equal to 0, which is what makes it true. And if you have any questions about using your calculator, let me know. All right, so what is this rule called? It's at the top of the page.
Zero
The
product.
zero product rule. And why do they call it the zero product rule? What are those zero product? What are they referring to? That if your product is equal to 0, you know something about these numbers. You know something for sure. You know that one or both of them is 0. And that's what the zero product rule states. Okay, let's keep going. That's it. That was my introduction to the zero product rule. So now we're going to do it. Now we're going to implement the full strategy. Everything that we've been working towards, all this practice of factoring techniques, was all so that we could solve these equations right here. So the factoring techniques are just a tool that we were using so that we can actually solve an equation. So we're going to take a look at 55. Let's take a good long look at 55. Let's say that it's the 1500s, and I walked up to you and I said, I'm thinking of a number that if you square it and then subtract itself, it'll equal 20. Okay, so imagine you're at a party and they're playing a party game. And they're like, okay, I got a good party game for us. I'm thinking of a number that if you square it and subtract itself, it equals 20. So first of all, just go ahead and guess.
5.
Very good guess, Deegan. 5 works, right? 5 totally works. Because 5 squared minus 5, that's 25, minus 5 is 20. So did Deegan get it? Is that a number that if you square it and you multiply and subtract itself, you get 20? Yeah. Now, I'm telling you, there's another answer. Find it. What's that? Oh, darn it, Mick just said it. -4. -4 is the other answer. Let's watch. -4 squared minus -4. Let's see. -4 squared is 16. Double negative plus 4. That's also 20. Now I'm telling you that's it. There were only two solutions. There are only two numbers in the whole universe that you could square it, subtract itself, and it would equal 20. And that solution is x equals either 5 or -4. Now, I just asked you to guess. Mick, did you guess?
I just guessed it first time, but honestly, I think of more. You do need to work.
Oh, okay. So you were just guessing. Okay, great. And Deegan, were you guessing?
I solved it.
Oh, you already solved the equation.
Yeah.
Oh, okay. Well done. Well, you can see though how you might have guessed, right? What would you have done to guess? Just start with 1. Like 1 squared minus 1, that's not 20. 2 squared minus 2, that's 2. 3 squared minus 3, that's 6. 4 squared minus 4, that's 12. 5 squared minus 5, that's 20. Ooh. Right? That would be the guessing process. And the guessing process is what they had going for them in, say, the 1400s, 1500s. They would just sit around and try to guess these things. They had some tools available to them, but not incredible. Okay, so if you didn't want to guess, though, what would we do? Yeah, let's bring the 20 back over. So go ahead, bring x squared minus x minus 20 equals 0. And now, here's the really key thing. Do you remember what we call this when you set an equation equal to 0? It's called what form? Standard form. This is standard form. Why is it standard? Why do you suppose we call that standard form? Why do we want something to equal 0? Why would mathematicians think it's so important that we set all of our equations equal to 0 that they call it standard form? Why do we want equations to equal 0? So that you can use the zero product rule. Only if something is equal to 0 is that a game that you can possibly win. If it was a times b equals 10, are you ever going to guess what two numbers multiplied equal 10? Never. But if it's a times b equals 0, now you have a fighting chance. One of the numbers has to be 0. So we call this standard form because it equals 0, because then you can use the zero product rule. All right? Now again, this might sound easy or obvious, but this was an invention in the 1500s, 1400s. This was new technology in the 1400s. That they were like, whoa, we should set equations equal to 0, because then we can convert addition problems into multiplication problems and solve them. That was mind-blowing at the time. So let's do it. Go ahead and factor it, folks. What two numbers multiplied equal -20 to add to make -1? It's 1 and 1. Factor table for 20, 1 and 20, 2 and 10, 4, 3, 4 and 5. Okay, that's it. And they have to have a difference of 1, so that's 4 and 5. And they have to add to make -1, so which one's negative? The 5. So now we have x plus 4, x minus 5 equals 0. So we take an equation, you put it in a standard form so it equals 0, and then you factor it. And now that it's factored, we can use the zero product rule. And we say something times something equals 0 only if the first one is 0 or if the second one is 0. And then from that, you easily get your answers. Which are the answers that Deegan and Mick guessed?
-4.
Yep, -4 and 5. Folks, this is the standard procedure. So if you wanted to write it down in terms of what we're doing for like the rest of the semester, the first step would be to write your equation in standard form. Write in standard form. And what is standard form? What is it? Something equals 0, right? So write it in standard form. Why do we write it in standard form? So that you can use the zero product rule. So you write it in standard form, and then you factor it using one of the many, many factoring techniques that we learned over the last few class periods. And then you set each factor equal to 0. Right? Once you're done factoring, you just set each of those binomials equal to 0, and then you just get your answer. And that is the solution for the original problem up above. There's something else that's really nice about this, and that is, look at the original problem. The original problem, x squared minus x equals 20. That's a hard problem. There's a squared term in there. That makes this problem hard. But look at the problems that you actually do solve for x. Those are easy. These are easy, easy, easy. When you actually solve for x, you know, when you're actually solving for x, is that a hard equation to solve for x? No, that's like junior high school level solve for x. Right? That's like the easiest possible equation you can solve for x. And that's, again, what this strategy does. It takes a really difficult, challenging polynomial, factors it into linear binomial terms, and then the only solving for x that you ever do is really, really simple. So that's another benefit of this whole strategy. Let's try another one. All right, we got a whole bunch of them. We have tons of them to try now. So go ahead and try 56 on your own, and make sure you're doing all those steps. Well, I guess it's already in standard form. But go ahead and try 56. Factor it, use little arrows to set each binomial equal to 0, and then solve for it. And then I would check it. Check to make sure that those numbers that you found actually did work. All right, let's check your factor work. What two numbers multiply to make negative 22? That would be, factor table is 1 and 22, 2 and 11. And we want them to be a negative 22, so we're looking for a difference that makes 9. So that's definitely 2 and 11. And then 1 needs to be plus, 1 needs to be minus, so the 11 is plus and the 2 is minus. So did you all factor it into x minus 2 times x plus 11 equals 0? Is that what we got? Did we? Okay, good. All right, so this times this equals 0. Therefore, I can force x minus 2 to equal 0. I can also force x plus 11 to equal 0 by simply letting x equal 2 or letting x equal negative 11. And that's it. The solution is x equals 2 or negative 11. Do they both work? Did you plug them back in? Do they really both work? 4 plus 36. Wait a minute. Oh, 4 plus 8. Wait. Does my 2 work? 4. Oh, there we go. 4 plus 18 is 22 minus 22 is 0. That works. And then negative 11 squared is 121 minus 99 is 22 minus 22 is 0. So yeah, they both do work. They both really do work. If you plug them in, it makes the equation true. Okay, how about the next one? 57. What do we have to do first? Yeah, take out a 5. That's always our first impulse. Can we factor something out? You don't want to have to do a harder problem if you don't have to. So the first thing is, can you take out a 5? And yes, we can. So that's x squared minus 7x plus 12. Did I do that right? No. Now, you might be getting to the point where you feel pretty confident with this and you think, man, I can just do this in my head. What numbers multiply to make 12 to add to make 7? 3 and 4. But I need them to multiply to make a positive 12, but add to make a negative 7. So it's not just 3 and 4, it's negative 3 and negative 4. Now, as much as you feel like you can do it in your head, I still think it's a good practice to just write it out. Because that way you're taking that burden off your brain, and you're actually just putting it all there on paper for your audience, your own brain, and now you can just see 5, x minus 3, x minus 4. Now, folks, this is interesting. Did we say the zero product rule was A times B times C equals 0? Do you think it still works then? Can you have 3 things being multiplied? Can you have 4 things being multiplied? If I have any product in the universe and it equals 0, what does it tell you about one of them? One of them, it better be 0. So now, right now, I have 3 things being multiplied to equal 0, right? And the question is, can I make any of them equal to 0? So can I make a 5 equal to 0? Can I like squeeze it hard enough and a 5 becomes a 0? No, 5 will never be 0. So 5 is pretty immaterial to us. 5 doesn't matter for the solution. It's just a number we factored out, and it's going to sit there and do nothing. It doesn't feel sad about its life or anything like that. It's just not part of the solution. So now, these are the 2 that we have to think about. Can they be equal to 0? And yes, those can be equal to 0. X minus 3 could equal 0 if x equals 3. And x minus 4 could equal 0 if x is 4. And so our solutions are just 3 and 4. 3 and 4 are the only 2 numbers in the universe that you can plug in to that equation, and it will make the whole equation equal to 0. The little 5 out front just not part of the solution. Yep. Okay, how about this one? 6y squared and 19y plus 10. Our first impulse should be to factor out the GCF, and is there one? No. Nothing goes into 6, 19, and 10. So that means we can't factor anything out, and we just have to do the kind of the longer method of non-basic factoring. So how do we start that? Yeah, take the first number times the last number. So 6 times 10 is 60. One of everyone's favorite number, 60, a good number. The factor table, 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10. So it's multiplying to make a positive 60, so we're looking at a pair of numbers that add to 19, which is it?
4 and 15.
Yeah, 4 and 15. All right, so now we still don't know the answer yet. All we get to do now is factor by grouping. So what do you want to do, 4 plus 15 or 15 plus 4? Because you can choose. Do you want to do 4y plus 15y or 15y plus 4y? Genesis, choose for us.
Doesn't matter.
Choose anyway. Do you want to do the 4 with the 6? Because then you can factor out a 2. Or the 15 with the 6, and you can factor out a 3. Which one? 4. Okay, we'll do 4. So 6y squared plus 4y plus 15y. And then we put on our parentheses, factor out what we can, and what can we factor out? 2y outside of 3y plus 2. And then here we can factor out a 5, so that's 5 outside of 3y plus 2. And we're left with 3y plus 2 times 2y plus 5. There's something very important that I didn't do to every line of the work that I've shown, that I should do, technically. Did I say it again? Yeah, make it equal to 0. I totally left that off. I really do need to include that equals 0. We're talking about an equation now. We're not just talking about some disembodied, ghost-like expression that needs to be factored. We're solving an equation. The thing equals 0. Now, now that it's equal to 0, we can set each of those equal to 0 and actually get our solution. So we have 3y plus 2 equals 0, or 2y plus 5 equals 0. And again, you might be able to do that off the top of your head, but show a little work anyway. And what are our 2 solutions? What's the first solution that you got? Emily? For 3y plus 2 equals 0, what did you get?
2/3.
Yeah, negative 2/3? Yep, negative 2/3. And then the second solution that you got, Amber?
-5 halves.
Yeah, negative 5 halves. All right. Well, folks, we did it. This is actually really very exciting. if you don't have goosebumps or tingles, I'll tell you why you could have had those. We just looked at an equation, 6y squared plus 19y plus 10 equals 0. And we just found out the only two numbers in the universe that you can actually plug into that equation to make it true. And if you did not know how to do any of that, and if I just told you to start guessing, would you have ever guessed negative 2/3 and negative 5x? You would have never guessed it. Not in a million years. And yet, using this fairly straightforward, simple process, yeah, anyone want to agree? This fairly straightforward, simple process, we can change a trinomial into a quadrinomial, factor by grouping, factor, and then set each binomial equal to 0, and bam, we have our answer. And there's no guessing involved. That's incredible technology. That is incredible technology that they invented. All right, now of course you'd still want to plug those in and see if they're true. We didn't plug them in, but you would want to verify your answers. Okay, well, we have just completed there some basic examples. Those are all some nice basic examples of the zero product rule. So let's look at some special cases. There are some special cases that I've given you here. So about that first one, number 59. 22n squared plus 6n equals 0. First of all, care to take a guess? I mean, probably we're not even motivated to guess. I mean, what would you even begin to guess? Would you guess a positive number? Would a positive number even be a good guess? Because 22 times a positive number plus 6 plus a positive number, that makes a positive number. And is a positive number going to equal 0? No. So we don't even need to bother guessing a positive number. Should we try guessing 0? Anyone? 0? Plug it in, calculate it. 22 times 0 is 0, plus 6 times 0 is 0, 0 plus 0 is 0. Yeah, 0 is a really good guess. 0 is the answer. 0 worked. If I plug 0 in there, it equals 0. Now, but is 0 our only answer? Is it possible that there's a negative number? That when you square the negative number, it becomes positive. So then you have 22 times that is a positive number. But then 6 times a negative number is negative. And you'll have a positive plus a negative. And might that balance out exactly to equal 0 again? It could. So again, there's going to be two solutions. Folks, how do we already know there's two solutions? Like, how do you know right up front there's two solutions? Not because there's two n's, but because the highest power on n is 2. The highest exponent tells you how many solutions there are. So the fact that that's an n squared, there's two solutions. So 0 is one solution, but you still have to find the other solution. Matt?
I'm going to ask if the exponent was a 3.
Yes, if the exponent were a 3, there'd be 3 solutions. If the highest exponent were a 4, there'd be 4 solutions. And just like you could all guess, if the highest exponent is in 1, how many solutions are there? 1. Yeah, so the highest exponent on x tells you the number of solutions. So any quadratic is always going to have 2 solutions. And that's what we're looking to find. So would anyone like to guess the negative number? Yeah, I mean, it's hopeless, isn't it? Guessing? Guessing would be fairly hopeless. Maybe if you had a calculator, you could sit there and plug in lots and lots of negative values until you finally get it. But nobody wants to do that. So what do? Yeah, what did you say? Yeah, we want to factor, right? Can we factor out a number?
Yes.
We can't? Yeah, we can factor out a 2. Can we factor out an n? Yeah, so look, we can factor out a 2n. What's left behind? 11n plus 6. Oh, sorry, plus 3, thank you. Did we just turn an addition problem into a multiplication problem? We sure did. This thing times that thing equals 0. So we just did it. We turned an addition problem into a multiplication problem, and we're ready to use the zero product rule. We can now go ahead and say that either 2n is equal to 0 or 11n plus 3 is equal to 0. Either of those will give us what we're looking for, which is the product to equal 0. And so what is one possibility? 0. That was the one that we guessed. And what's the other possibility? You move the 3 over, that's a negative 3. You divide by 11, negative 3 11ths. Were any of you going to guess negative 3 11ths? Probably not. I mean, none of us were going to guess that other solution. Oh, Manuel, he guessed it. I take it back. You got it. But for the rest of us, we would have to factor and then use the zero product rule to set each binomial equal to 0 and solve. Okay, now number 60 is a good question. What do we do? Is it already a multiplication problem? It's not a multiplication problem? Is it not x times x minus 1? Is that not a multiplication problem?
Before it's not equal to 0.
It's not equal to 0. Yeah, that's right. It's not equal to 0. In this case, folks, could I just set both of those and say either x equals 42 or x minus 1 equals 42? Would that be appropriate? Yeah, that's a misuse of the zero product rule. You only get to do the zero product rule if it's something times something equals 0. And this is something times something equals 42. That doesn't give us meaningful answers at all. Could 42 work or could 43 work? No. 42 times 42 is not equal to 42. So that didn't work. This is not equal to 0. How do we make it equal to 0? Jesus? Yeah, let's distribute first. We'll have to distribute. Well, maybe you're convinced of that. Maybe you're not convinced of that. But we distribute, and then what? Plug in numbers? Oh, so just start guessing? We could. To tell you the truth, you guys could probably guess this. What two numbers are right next to each other that they multiply to equal 42? I can just ask you, what numbers multiply to make 42? 6 and 7, right? And so 7 times 6, if x is 7, then 7 minus 1 is 6. And did we already guess? We guessed one answer. X is 7 is one of our answers. But we don't have the other guess yet. Okay, so now what do? We distribute that? Yeah, we got to move that 42 over. No matter what, we have to make it equal to 0. There is nothing we can do until the equation actually equals 0. Okay, now you can factor. What multiplies to make 42 that adds to make 1? I should say that differently. What multiplies to make negative 42 whose difference is, there we go, whose difference is 1. Yeah, 6 and 7 with the negative 7 and the positive 6. So now this is really x minus 7, x plus 6. Notice I'm keeping my equal 0. I hope you are too. We want to keep that equal 0, equal 0, equal 0. You always want to keep it, the whole thing as an equation. So now I can use the zero product rule. This thing times this thing equals 0. Therefore, either I can make x minus 7 equal 0, or I can make x plus 6 equal 0. And therefore, x equals 7, which was one number that we could have guessed. If we had just thought what times the number 1 less than it would equal 42, that would have been 7 times 6. This other one we might not have guessed, negative 6. Does that work up here? If I let x equal negative 6? What does that become? If x is negative 6, what's x minus 1? Negative 7. And notice, it's still 6 times 7 equals 42. But what do you notice about the 6 and the 7 now? They're both negative. So that's how you got that extra possibility. That when you have a quadratic equation, x squared, you have 2 possibilities. Because even though 7 times 6 was an obvious guess, negative 6 times negative 7 also works. And so quadratics have 2 possible solutions. All right, well, folks, this is fun. Just from my own perspective, I love the zero product rule. I think this is very clever. I think this was wonderful technology they invented hundreds of years ago to set an equation equal to 0. I mean, just imagine it. That changed how math was done. Someday, one morning, they woke up, they said, what should we try to do? And they said, make the equation equal 0? And it was a good guess. And that changed how we did things. All right. Folks, what time is it? We're about to transition from just trying it to doing word problems. When do we normally take a break? 1:30? 1:40? I totally forget. I was going to say now would be a good time to take a break. My phone didn't go off yet, but I think now would be a good time. Yeah, we normally go at 1:40. Let's do it now because we just finished trying it out. The next thing we're going to do are word problems. Let's take a break right now. It's 1:25. Let's all be back at 1:35.
both those down and highlight.
I would have said.
But the guys more, I just can't.
Qué bueno. ¿Qué horario tiene?
Jen, do you speak Spanish?
Yeah.
Oh, because I thought you were speaking English, but that one sounds like, wait a minute, she speaking Spanish. You're just going back and forth.
Spanish.
Right, one button. Were you watching the video here? Okay, you're saying you couldn't see it.
Yeah.
Okay, well, that's fine. So what do you think is? What's that? Okay. Well, I went back to do it today, so hopefully this one's gonna work out.
Okay.
I just need to get it right. Just ask somebody to borrow it up. I bet somebody would be nice. If not, you go upstairs. Somebody will be nice. And then you can do it.
Mira. Mira.
That's the only thing.
Oh, I
What did you get? 60.
Yeah, but that's not there.
That doesn't matter.
Oh, yeah, you
This
did.
one
So
doesn't
X
matter.
squared minus 4. And then minus 6.
This one, you know, factor.
And so now you have X squared
Yeah, but that
minus
one.
64.
Because it doesn't have a, it's not.
That's not an X on the board. That's just 4. That's really X squared minus 64.
Oh, no, I'm getting
Because this one.
No.
Wait, what?
No.
But that one.
Yeah, that is really 4. It's X plus 2 times X minus 2 is X squared minus 4.
Okay,
So
so
X squared minus 4 is
puedes
64. So now, minus 4 minus 6.
You know what I'm trying to say?
Right, guys, did you just make a mistake?
This is very part of
Oh,
it.
and wait.
That could be. Let's find out. Over 56. Right here. This is the one we did earlier. Okay, so plus 9 and minus 22, and 11 and 2. That seems to be yes, and then it's
Okay, so you know number 59 and number 57? You know how we factor 5? And it's like, that number doesn't matter, right? Okay, then why in number 59 we factor a 2 and
Because it has
as a variable? So if it has a variable in front of it, then we count it? I mean,
because remember he said that if there's
So are you plugging
a
in
square
negative 11 into that and then
primary
or you
square
plugging
Oh,
it's 3, 4, 5.
it's 2 solutions. So basically, it would have just left, it would have ignored this, and it would have just kept this as just one solution, so you have to. Oh.
Okay, well, this one. So
I was like, what's going on?
positive 11 should be the answer. Because so positive 11 squared is 122. Yeah, so that's 2. And positive 9 times 11 is 499.
Yeah, but that's good.
So far,
And also,
and then if I subtract 22, well, that can
that's
So definitely 11 is wrong. Now tell me why.
okay, how can you tell the
Oh,
difference
you're saying it's
between,
positive 11 because of.
non-basic,
Because I was gonna say.
basic, non-basic factors and just greatest common factor? Because like,
Because you cannot find a greatest common factor all three polynomials, then
Okay,
you
now,
do
look over here. What kind of did you
what I'm saying?
Yeah, so
Like,
then you have to do
the non-
non-basic. Okay, and let's just say for, you have the number one for the quiz, right?
Okay.
It's
So
just
now go
greatest
back and
common
double check
factor.
this one. Convince yourself it's 11 with
Oh, it's just the
negative.
thing is that I don't messed up because you know how
Sweet,
like
good question.
you took the greatest common factor and then you know the parentheses, the middle part. So I thought we had to like simplify or factor it more. So I was like, okay, I don't have any common factors. Let's start with non-basic.
The way it goes is you take the root of factor, you take whatever and then figure out what that's 15 is. Right there. And then you subtract the x's.
The x's.
The x's. So yourself as we add the x's. Here, this will give you. So the process is dividing, subtract. Make sure outside variables.
The outside
And
variable.
then you use number and then all you do is you just take that outside variables and then you divide the whole number.
And then subtract the exponent.
Yes.
Oh,
Remember, divide, subtract.
I know how to do this. It's just that I can't tell the difference.
Okay, well, let's see.
Like I'm worried because on the test, I'm like,
Oh, I know, you're gonna have to know.
like what is he gonna mention? Like he's gonna like find the
problem.
and then the problems he's just gonna like find the
That's why I
common
need to work.
factor, or is he just gonna be like
Here you go, solve it.
solve it?
When I saw it, it's not hard.
LA Fitness is expensive, US Fitness is just paying $20. Yeah, it's like,
I hate EOS.
okay.
Why?
It's so small.
It is small.
They got a lot of stuff, but it is too small, yeah. That's just bad.
I don't like it.
I canceled.
I rather just have the essays.
Yeah, you know what?
It's big.
It's spicy, but it's probably good, yeah, after like
It's
switching,
big. You
yeah.
have your own little bubble.
Really, yeah, like it's huge.
You go to
and it's
AOS
like-
and it's scary.
I know, and you're like,
And it just like looks cool.
like this little thing. Yeah.
Because I was looking at it's like
My brother was $50, but it's like the membership where you have to bring two guests with you. I think that's pretty cool. I don't know what I'll ask what membership.
But like, I'm not sure, like even you fit cheaper, but it's not equipment worth it. It's like men wanting to do like some and stuff like that. But I know LA Fitness, they provide.
Yeah, I know.
Yeah, that's the one. It's big and you don't feel claustrophobic.
I like it's like everyone can spread it.
Yeah, and not
I
like
like each other.
no one's using the
Sound,
same
the
thing.
sauna.
Yeah.
It's a sauna, and then
Depending on the location.
yeah, depending. It's like the pool, and then it's always a sauna room, and then it's separate. It's like separate, like girls sauna, boys sauna. At EOS, it's like one room for both genders.
Yeah.
Yes.
no type of gyms I've like that.
All right, folks, let's get going. We'll just yelling all in the juice.
Yeah, those are the ones that form Chicago. Hey, you can't. Fucking out.
Oh my god.
What, you're like, shake your head like,
Not really.
All right.
wow.
Folks, 135, let's continue class. So we're all on number 61, right? What two numbers multiplied equals 61?
60 plus 1.
61.
Does anything multiplied equal 61?
1 times 61.
61 is a prime number. So nothing will multiply to equal 61. Not a whole number anymore. You're right, if it was a decimal. Okay, so let's take a look at 61, folks. Now, you recall the 4 steps of word problems that we were doing before? Wait, did we talk about the 4 steps of word problems?
No.
Oh my goodness. Well, I'm going to go through 4 steps of word problems with you. 1, 2, 3, 4. Now, obviously the first step is to read the problem, but that's a given. So let's just read it real quick. A rectangle has a length of x plus 2 and a width of x minus 2, and it has an area of 60 units. Find the length and width of the rectangle. Okay. The first time you read a word problem, you know, at best you kind of know what you're talking about. What are we talking about?
Rectangle.
A rectangle. Okay, so we got some problem about a rectangle. We know how long and wide it is and what the area is. The first thing you want to do in a word problem is draw a picture. We want to draw a picture. Oops. Draw a picture. So let's draw ourselves a really nice picture. This is basically always true, that if it's a math problem, you need to draw a picture to model whatever's happening. So I'm going to draw a rectangle. How did I do?
No, it's good.
Does it look good? Is it the best rectangle you've ever seen in your whole life?
Very
Yes.
possible.
Yeah, it's very nice. Would this have been a good rectangle?
No,
No, what does that look like?
square.
Oh, it's like a square. The problem's talking about a rectangle, not a square. Make sure your rectangle looks like a rectangle, not a square. I'm serious. Because otherwise your brain will play funny tricks on you and you'll think it's a square and you'll treat it like a square and you'll think the side lengths are the same and they aren't. So make sure that when you're drawing a picture, it looks like what you say it is. All right, so a rectangle has a length of x plus 2 and a width of x minus 2. Should I put x plus 2 here and x minus 2 here? Or should I put x minus 2 here and x plus 2 there? Is this labeled correctly right now?
Yes.
It is?
No.
No, it's the other
Why
one.
not? Yeah, I mean, this is the long one, so that should be the plus 2 and that should be the minus 2. So again, we just want to make sure we're drawing good diagrams, really good diagrams that are realistic, and not just throwing numbers anywhere. So it's got a length of x plus 2, width of x minus 2, and the area is 60. So I'm going to write A equals 60 inside. Okay, well, it says find the length and the width of the rectangle. So are we trying to find x? I mean, sure, we got to solve for x eventually, but what do we really want to know?
No length.
The length and the width. So our final answer is not going to be x equals 7. It's going to be a length and a width. That's our final answer. Okay, we've completed step 1. We drew a nice picture. Now what do we do? We need to build an equation. Because most word problems are not going to give you the equation. They're going to expect you to come up with the equation and make it yourself. So what concept are we even looking at here? We're looking at the concept of what? Area? Yeah, and what's the formula for area? Yeah, area equals length times width. So that's our formula, length times width. I use a cursive L, so it doesn't look like a 1. So area equals length times width. Let's go ahead and plug in what we know. So I know that my area was 60, and I know that my length was x plus 2, and my width was x minus 2. How's my formula? Yeah, I think it looks pretty nice. I think that's pretty good looking. You know, I think we did it. What's that, Manuel? Oh,
I
no.
was just laughing.
Oh, okay. Now, I might do one thing here, though. I don't really like having the 60 over here on the left. You know what I'd really like? I'd really like to have all my variables on the left and then the 60 on the right. And there's no reason I can't do that. I'm going to go ahead and make it x plus 2, x minus 2 equals 60. Why do you suppose I'm going to do that? Why would I go ahead and just switch the right and left-hand side of the equation like that? It makes it easier because what am I trying to do eventually? Yeah, right. I want the whole equation to equal 0. So I might as well start my formula with everything on the left where I need it to be. Okay, well, we did it. We built an equation. Those are the first 2 steps. That's the pre-work. Okay, that's the pre-work just so we're in a position to actually solve the problem. So now what are we actually going to do?
So
The age-old classic, solve for x. All right, so we're going to go ahead and solve for x. So in this particular case, can I go ahead and use the 0 product rule right now? No, because it's not a standard form. It's not equal to 0. I can't say this times this equals 0. I could say this times this is equal to 60. I could play around with that for a while. I could think, what 2 numbers multiply to equal 60 where, you know, they're 4 units apart? You could play around with that if you wanted to, but let's just solve it. Since it's not in standard form yet, I need to bring the 60 to the left, And I have to do what to this thing? I need to make it look like a normal quadratic equation, ax squared plus bx plus c. I need to make it look like a trinomial so I can factor it. So what do I need to do with my two binomials here? FOIL. We have to FOIL. That'll always be the way. You need to FOIL, distribute, multiply, bring everything to the left. Then you're in a position to factor. So what happens when you multiply conjugates? The middle terms cancel out, so we just have x squared minus 4 equals 60. And then we go ahead and bring the 60 over to the left. So minus 60, and that gives us x squared minus 64 equals 0. All right, so now we want to factor this. Now just so you know, there's at least 3 different ways to solve this problem. I'm just showing you one of the particular ways to solve the problem right now. So if in your head right now you're like, Mr. G, I wouldn't be doing that. I'd be doing it this way. That's fine. We'll look at all 3 different solutions. But this is the one I want to show you. So what factoring rule are we going to use now? X squared minus 64? Yeah, this is our difference of squares strategy. We have a square number subtracting another square number. So this is actually x squared minus 8 squared. And so how can we rewrite that? What is the rule for the difference of squares? Yeah, x minus 8, x plus 8. This is the product of conjugates. So x minus 8, x plus 8. And now we're in a position to do difference of squares. I'm sorry, we're in a position to do the zero product rule. Isn't that crazy? We started off with something that was already a product, but it wasn't equal to 0. So we couldn't do the zero product rule. So what? We had to FOIL it out, bring everything to the left, and then factor it. Now we can actually do the zero product rule. In life and in math, we call that sometimes it has to get worse before it gets better, right? We had something that was a product, but it wasn't 0. So we had to do a lot of manipulation to make it a product equaling 0. So now what do? Set both of those equal to 0? Because either x minus 8 is 0 or x plus 8 is equal to 0. And I can make x minus 8 equal 0 by making x equal 8. Or I can make x plus 8 equal 0 by making x equal negative 8. Are we done? We're done solving for x. The next thing we have to do is verify truth. Right? That's the end of every algebra problem, is you check to make sure that it makes a true statement. So what are we verifying? What was it anyway that we were trying to find? The length and width of the rectangle. And whatever length and width of this rectangle is, the area better be 60, because they told us that right up front. This rectangle has an area of 60. So let's try both of our solutions. Does 8 work? If I make a rectangle and I do 8 plus 2 and 8 minus 2, that gives me 10 and 6. Does that rectangle have an area of 60? Yeah, so that worked. So definitely x equals 8 is one possible solution where the dimensions are 6 by 10. Right? Notice I'm giving like a compound answer. I'm saying if x equals 8, the dimensions of the rectangle are 6 by 10. All right, what about our second number? Will it work if we do negative 8? Negative 8 plus 2 and negative 8 minus 2. What's that? Negative 6 by negative 10. Is negative 6 times negative 10 equal to 60? It is. Is the area equal to 60? It is. But can you have a rectangle whose side length is negative 10 and negative 6? You can't. Because negative numbers don't make sense. So x equals negative 8 is an extraneous solution. Extraneous. Extraneous is a word that means mathematically true, but nonsense. That's what extraneous means. Negative 8 really does work to give us a rectangle whose area is equal to 60. It's true, the area is 60. But does it make any sense for a rectangle to have side lengths of negative 10 and negative 6? No, it's nonsense. So our final solution would be x equals 8 gives us the dimension 6 by 10, and x equals negative 8 is extraneous. So how many actual solutions are there? Just one. Even though I just sat here a little bit ago saying that if it's x squared, there are going to be 2 solutions, it just said that a little bit ago. Am I already a liar? If it's x squared, there's two solutions. Were there two solutions?
Yeah.
Technically, there were. There were two different numbers I could plug in for x that gave an area of 60. So yes, there were two solutions. It's just that one solution is extraneous, meaning it's nonsense. Okay, well, really nicely done, folks. That's our first problem there. Did we do four steps? We drew a picture, we built our own equation, we solved for x, and then we verified the truth? That's a long problem, isn't it? That's like a good, lengthy, meaty problem. Feelings? Yes.
I have a question.
Great, Lilia.
Answer on the back, you put what it was the six to with. Is that how you want us to write it like on the test, or do you want us to do the x?
Now that's a really good question. Honestly, you only have to just answer the question. And the question was, what are the dimensions of the rectangle? So the answer would be 6 by 10 or 10 by 6. Yeah, either way, that's what I'd be really interested in. Because if you told me it's 10 by 6, you must have figured out x along the way. Yeah, so just the 10 by 6 is fine. Okay, folks, I said that there were two other ways to solve this problem. Did one of you already try to solve it a different way? Then you want to share that with the group? Anyone? Well, I tell you what, here's one other solution. Do you remember when we were here at x squared minus 64 equals 0? How could we have solved that differently?
By squaring negative or squaring positive 64.
Yeah, couldn't we have just taken x squared minus 64 and just went straight to x squared equals 64? You know, just move the 64 back over, and now we have x squared, so we can square root both sides. And whammo, x equals plus or minus 8. Would that have been faster?
Yes.
Could have been considerably faster. That wouldn't have been the purpose of this chapter. The purpose of this chapter is for us to work on factoring. But yeah, that would have been much faster. That would have given us the plus 8, the minus 8, and then we would still have to plug it in to verify the truth, but that would have gotten us the answer much faster. On the test, do I care which way you do it? No. Yeah, so probably right now you guys are all like, well, I'm going to do it this way next time. And that's fine. You know, this one worked out. You could do it this way. You won't always be able to do that. Jesus? Oh, he did? Okay. Oh, the fact that you could do that on the test? Yeah. Now, but here's another way to solve this problem, which is super exciting. And now that you're all experts at factor tables, we wanted the area to be 60, right? And we wanted the lengths of our rectangle. How many units apart are those lengths? How far apart is x minus 2 and x plus 2 on a number line? 4. It's 4 units, right? If you can't see that just by looking at it, that one is right 2 and one is left 2, you could just plug in a number. Like 10 minus 2 would be 8 and 10 plus 2 would be 12, and 8 and 12 are 4 units apart. Well, so we want two numbers that multiply to make 60 that are 4 numbers apart. So, do you see them? Which two numbers multiply to make 60 that are 4 units apart? Which is it? 6 and 10. What are the dimensions of the rectangle? 6 and 10. Who liked that solution? It's a pretty nice solution. You can't do that on the test. I won't give you any credit for that on the test. Because in this class, we're working on our factoring techniques and the zero product property. So this solution is incredibly clever. It's a very clever solution. Like, bam-o! You just found the dimensions of the rectangle were 6 by 10. But it didn't demonstrate what the skills are that we're working on. So if you want to do this to verify your answer, like if you want to do that just to feel good, like, okay, I know the answer is 6 and 10. Why is my math not working out? Then sure, you could do that. You could do it this way. But to earn credit on the test, you have to show me the zero product rule or square root property or something like that. Okay. Other thoughts or questions for all this? All right. Well, that's a really good question. Let's try another one. In fact, all of you go ahead and try it. A rectangle has a length of x plus 3 and x minus 3 and an area of 40 units. Find the length of the rectangle. Go. You can do it any of the 3 methods. Of course, when I say you can do any of 3 methods, what do you think I really want you to do?
The longest one.
All 3. I want you to try all 3. Try all 3 solutions out. See how it works for you. Now, by all means, you can talk with your neighbor. You can work with someone near you. Let's take 5 minutes and work this solution out.
No, you can just do a fact table and see which numbers in there are alpha. You can actually, what is that? You know this.
So you said something.
That's it wouldn't hurt just to-
Oh, yeah.
I'm just saying. You can go ahead and- You might hear it. It's real hard. That's how you- Yeah, just like you think. That's perfect. Very nice. Hey, so did that one work out? Yeah, okay, so you guys, which of the three methods do you like? Oh, for, sure, that is nice. Good. That's right. Ooh, you're trying to- I am, this is so. Very nice, very nice. Hey, that
Oh, she works. She's a manager, dude. She works, I guess, so she. She's a manager. I didn't know she was, she's been working.
Oh, I almost there. I gotta go. Which method did you like better, one, two, or three? The factor. Oh, I like that. Very good, nice. Denison? Looking good. Hey, looking real nice. Oh, yeah, very good. I like that you did oil there, really nice. Oh, great. Check your head out.
And then she's been working for years.
It's really good. I like how you plugged it in again. Find your liking. That was really good. Hey, and you even did the factor table. And it give you the same solution? Cool. Nice drawing, Chris. Oh, very nice. Over here, you got your thing, and then that equal the 40, and you move that over, and then that, and then the factoring. That's a 7 squared, right?
So yeah, right here is where I was kind of stuck. So after this,
You bring the 49 back over to the left. Yeah, so it's x. You actually do it. Cross out those 40s right there, because that's a 40 minus 40, that's 0. You actually have x squared minus 49 already. You wrote x squared, and then you put the minus 49 over there. You have the minus 49 over there with the x squared. So technically, you have the work that you're showing leads to this. Oops. Oh boy, I'm
it's really
sorry.
sensitive.
There. Yeah. So right, because the 9 and the 40 are already on the left-hand side of the equal sign.
Yeah.
So it has to stay on the left-hand side of the equal sign.
Okay, I get
Yeah,
it.
that already canceled. That was 0. So there you go. You had x squared minus 49, which is x squared minus 7 squared, which is x plus 7 minus 7 equals 0. And put the equals 0 there. Yeah, really nice, Chris. That's all correct. And now you're going to draw your little line for there and your little arrow for there. Oh, you did it over there. Yeah. You got it. How's it going, Ingrid?
I think I.
Yep, you got a nice diagram there. You foiled it all together. Very nice. Brought that over to there. And then you went ahead and that's a 7 squared, right?
Oh yeah. Oh yeah.
Yep, very nice. And then you factored it that way. Perfect. Looking good. And so now you're going to plug those in to the original to see what the actual measurements are. Dean, how'd it go? Yeah, that's it. Evan, you did both methods.
Folks, thank you very much. Your work looks great, like so great. I'm so impressed. And if I haven't called you professionals yet, you folks are a bunch of professionals, I can tell. I would hire any of you based on the algebra that you're showing. So, which of the 3 methods did you like best? Did you try more than one method? So one method was factoring. The other method was the square root property. And then the other method was the factor table. So who likes the factor? Who did the factoring method or liked the factoring method the best? I know at least a few of you did. Okay, cool. How many of you just moved the number over and then square rooted both sides? Okay, good. And then how many of you tried the factor table? A few of you guys? Yeah. Okay, cool. So what are the dimensions of my rectangle? Yeah, 4 by 10. Yeah. Yeah, exactly right. So just walking around the room, I already saw your work. I don't think we need to review the problem as a group, but it looks really good. Now look at your own work. Did you draw a picture? Did you build an equation? Did you solve for x? Did you verify the truth? That's what I'm looking for to give you full credit on a test or a quiz. All 4 of those elements. Yeah, really nice, folks. Now, how do you feel about this word problem? Pretty good, I hope. I think just walking and looking at your work, you feel pretty confident and good. A lot of word problems are just like that. Very straightforward, simple. Every once in a while, word problems are a little harder. And that's what these next 2 are. They're a little more challenging. So now, maybe I shouldn't have said that. I don't want to psych you out. I don't want to psych you out at all. Maybe I shouldn't have said anything. Maybe I should have said, this next problem is even easier, and just left you with that. But I'd like you all to begin by reading it and coming up with what you think is a good picture. Don't even try to solve it yet. I just want to see a really good picture. Okay, so like pretend it's a test, and I say, I'm not looking for an answer. I'm looking for the best picture that describes this word problem. That's what I want, a picture. A really good, well-labeled picture. So everybody, we're all looking at 63. Read it and draw what you think is a good picture that captures what's happening. Take one more look at your picture and make sure that you've utilized all the numbers. You want to label everything. So whatever you're drawing is, you should have a number 20 on there somewhere, a number 13 on there somewhere, and a number 234 on there somewhere, and probably what else should you have on there? A variable, right? Somewhere on there, a variable to represent what we're trying to find. What are we trying to find? What's the question?
How wide is the path?
How wide can the path be? So, do we know how wide the path is? No, therefore the path is x. So somewhere on there, on your drawing, you should have a 20, a 13, a 234, and an x to represent what's happening in this problem. No, folks, there's no stress here. Okay, I'm challenging you to come up and picture yourself first. But, we're gonna go through and draw it together. I just want you to try it on your own.
That's how I have it. Equal width.
Okay, so I just walked around the room. I saw lots and lots and lots of different pictures. These were 5 different pictures that I saw while walking around the room. This is great. This is fantastic. I love the fact that you guys all came up with so many different interpretations and ideas about how to capture this information. That's really exciting and fun. Let's read the question. A rectangular garden. Stop. What should the garden look like? A rectangle. And absolutely all of you had a rectangle. All right. Has dimensions of 20 by 13. Just about all of you went ahead and put in a 20 and a 13, which is great. So they're 20 by 13. A gravel path of equal width is to be built around the garden. This I found really interesting. One person I saw, they drew a gravel path right there just to kind of represent the fact that there was a gravel path. They didn't draw it all the way around. They just kind of put the gravel path there and they're like, okay, yeah, there's a gravel path. Another person drew gravel. There's just kind of gravel littered about. It's not like a definite demarcation, but there's like a gravel path around it. That was fun. Another person, the gravel path was a windy route. It was kind of going around the garden. Like, that's fun. Like, isn't that a garden you would want to go to? To kind of spend some time and relax and kind of wander. And then another person took a gravel path like this. So, again, isn't this fun? These are a lot of really good and interesting interpretations. Okay, how wide can the path be if there's enough gravel for 234 square feet? So what's the question asking again? How wide can the path be? So that would be describing this width, at least I'm assuming if I interpreted your drawing correctly. So this width right here, that's x. And then probably this thing right here, that width right there would be x. And then in their drawing, this path right here would be x. And then in this drawing, this path right here would be x. This drawing, I don't have anything to label as x because there wasn't necessarily a path around it. But that's okay. You guys can all update your drawings as we go. So which one of these drawings do you think it's supposed to be?
The last one.
Why do you say the last one?
Because it's talking about the gravel path of equal width to be built around the garden. So if you want to go around the garden.
Yeah, so we do want to go around the garden. I mean, maybe this one stands out because it's so lame.
And it's actually square footage.
And there's some square footage we could calculate. Like, for instance, do we have a way to calculate the area of a windy path? We have no tools for that. We have no ability to calculate the area of a windy path. This one also basically works. We just don't know how wide it is. Or maybe even just by putting that boundary there, then it would become the boundary path we were looking for. And this one, this drawing just needs to be finished, going around the whole outside. But yeah, probably this drawing is the drawing that they intended, because it is a garden with a path going around the outside of it. So far so good. Update your drawings. And I'm going to go ahead and start drawing mine over here. I loved all of your drawings, folks. They were all very good. The only drawing that would have been bad is if you had drawn nothing. Right? Always just draw something. Okay, so we have I'm going to go right here. Here's my garden. And then here's my gravel path, which I'll make kind of wide just so I have something to work with. And what numbers do we know? 20 by 13 and 234. Okay, well, where does the 234 go?
Within the
It says, how wide can the path be if there's enough gravel for 234 square feet? Where does the gravel go?
side boundary.
Does the gravel go out here? Or does the gravel go in here?
Out.
Yeah, hopefully outside, right? Because what's inside? A garden. That'd be a really weird garden if it's just covered with gravel.
I mean, you could have a gravel garden, right? In fact, that's what most cactus gardens are. You got cactuses growing up out of gravel, so that'd be fine.
But in this case, we're saying the gravel path. So this is our gravel. And how much gravel do we have? We have enough for 234 square feet of gravel. So which area am I labeling 234? Yeah, the gravel. So this area is 234. And the area of the strip, the area of the border going around the outside. What's the area of the garden? What is it? What's the area of the garden itself? 260, right? 260, the area is length times width. So if I just want to find the area of the garden, length times width, that would be 20 times 13, which is 260. So what do we know so far? We know a lot. We know that the area of the garden is 260 square feet, and the area of the gravel path is 234 square feet. Whoa, that sounds interesting. How big is the garden compared to the gravel path? It's bigger. It's just barely bigger, isn't it? Isn't that a lot of gravel path for the garden? I mean, they're almost the same size, darn near. But I guess that makes sense because this path is going around the outside, and the garden is taking up all the space on the inside. So that's possible. Okay, there's one more thing I didn't put on the diagram yet. X. Where do I put X? The width of what? The path. Yeah, the width of the path. Everybody get in there, draw like a little arrow line right here, and call that X. This is X. And in fact, even the up and down portion, that's X. And this portion, that's X. How does our drawing look so far? Okay. All right, I'll take it. It's okay. I think it's pretty good because we've captured all the information that they gave us so far. In fact, we did. We captured all the information they gave us. Is there anything we left out? A rectangular garden has dimensions of 20 by 13. A gravel path of equal width is built around it. How wide can a path be if there's enough gravel for 234 square feet? Yeah, we did it. We captured all the information from the problem. So now what? Take a nap? Take a break? Sure. I mean, we just did a lot of work, and have we even begun to solve the problem?
No.
No, not even at all. All we did so far was wrap our mind around what the problem said. So what are we trying to find? X. We just want to know how wide the path can be. Well, how are we going to do that?
Build an equation.
Yeah, very good. We're ready for step 2. We're done drawing the picture. Our picture is awesome. Now we need to build an equation. So what would our equation be? What concept are we dealing with? What concept are we dealing with?
Length times width.
Yeah, area. Area is our concept. We're talking about the area. So we know that we're dealing with area. I'm not going to write area equals length times width. I'm going to write length times width equals area. Why am I writing the formula backwards? It makes it easier. I want to have all my variables on the left-hand side, and I just want to have the area over there on the right. Well, so now what? Plug in things, right? Well, so we already have the rectangle. Is that going to help us out? Do I plug in 20 by 30 or 20 by 13 right now and get 260? Well, sure I can, but did that help me solve for X?
No.
No. So the inner rectangle is not the answer. What about the outer rectangle? Do we know the dimensions of the outer rectangle? How wide is it? How tall is it? Do we know? How wide is this rectangle?
20 plus X.
Yeah, right? Look at it, folks. It's definitely 20 units wide, right? But then there's an extra X wide here, and there's an extra X wide here. So how wide total is it? It would be X plus 20 plus X. Is that fair? The total width all the way across is X plus 20 plus X. Jot that down on your picture. X plus 20 plus X. That's how wide the big rectangle is. And we can simplify that. Who said that? Was that you, Eduardo?
Yeah.
Yeah, Eduardo said 20 plus X times 2. Just to simplify that, we could write down what? Combining like terms? 2X plus 20? That would be the traditional way of saying it, to put the variable first. Yeah, thanks, Eduardo. Okay, folks, how tall is the garden? Yeah, is it 2x plus 13? Following the same reasoning, it's 2x plus 13. So now the total garden is 2x plus 13 tall. Okay, so now we have the outer rectangle. And the outer rectangle, we know, is a length of 2x plus 20, a width of 2x plus 13. And what's the area? Okay, let's plug that in. What's the area of the total rectangle? What's the area of the big rectangle? Is it 260? Is it 234?
234.
234? 234 is the area of the whole rectangle? We would have to add them together. What's 260 plus 234? We just did step 2. We just built an equation, and just take a look at the equation and see if it really resonates with you and where we got all that from. This was the equation for the inner rectangle, which was essentially worthless to us. The inner rectangle, there's nothing there to help us solve for x. But now we have an equation for the outer rectangle, and that has x in it, and it's an equation, and we can solve it. Where did the 494 come from again? Okay, yeah, that's the total area. JR, what's 234 plus 260? Yeah, because that's the total area. You've got the area in here, and you've got the area around the outside. So that's the total area of the total rectangle. Now, folks, at this point, if you wanted to make yourself a new little rectangle, just to show yourself that, the outer rectangle is 2x plus 13 by 2x plus 20, and the area is 494. Now, to be fair, the author of the textbook or this particular software, they could have just said, you have a garden whose length is 2x plus 20 and width is 2x plus 13 and total area is 494, solve for x. Is that the problem they could have given us? Yeah, that's the same problem, right? But then that would have taken away our joy. The joy of reading that problem and figuring out this actual scenario. And plus, this scenario is real. This is a real scenario. You know, you go down to Home Depot and you buy enough gravel for so many square feet, and then you go home and you want to put it around your garden. This is the type of calculation you would do. Of course, would you really do the calculation, or would you just start putting out gravel? Probably you just start putting out gravel and see how you do, right? But this would be the calculation of how you would do it. So are we ready to solve a problem? Oh boy, we sure did. We sure are. So what do we do? Is it something times something equals 0? No, it's not equal 0. So we're going to have to FOIL and then move the 494 over. All right, so FOIL and then move the 494 over. Folks, this is a good problem because it's epic. This is a good epic problem. It takes a little bit of time and thought and consideration. Okay, let's compare answers when you're done foiling and bringing the 494 over. So once you're done foiling and combining like terms and then bringing the 494 over to the left, does someone agree with me? Did I get that right?
Yes.
You think so? I think I did. Did y'all get 4x squared plus 66x minus 294?
Yeah.
Okay. All right, well, what do we do next? Now we have a genuine quadratic equation set equal to 0. We can use the zero product rule as soon as we factor. So what should we try to do first? Take out something. right? They're all even. Can we take out a 2? For sure we can take out a 2. Can we take out a 4? We can? I would love it if we could take out a 4. Should we take out a 4? Why not? The 66 not divisible by 4. I don't know if 234 is. Is it? I don't know. No. Okay, so we can't take out a 4. We can just take out a 2. Let's bring that 2 outside and just look at it for a second. Hi, 2. What is 234 divided by 2? 167? I think I did that wrong. Is it 167? What's 234 divided by 2?
117.
Oh, 117. I'm way off. There we go. 117. All right. What are we going to do with that 2? We could leave it. We could ignore it. Both of those are correct. What would be something nice we could do to get rid of it? Do what? We could just ignore it, but we can definitively get rid of it. What could we do? Divide both sides by 2, and it's gone. So now we don't even have to worry about it. That 2 is gone. It's not part of our problem anymore. And so now we have 2x squared plus 33x minus 117 equals 0. Okay, now are we ready to factor? We're ready to factor. There's no way around this, folks. We get to do the non-basic factoring technique. We're going to multiply a times c, rewrite the middle term, factor by grouping, and then eventually do the zero product rule to solve for x. Just a quick check-in with your emotions. Did you expect that any of the problems we would do would be this long? Oh, you did? Oh, you didn't? And maybe you're not feeling like this is very long. Maybe you're like, no, this is fine. This is great. This is a good problem. This is the kind of problem that you can definitely expect to be on a test or on a final because it's such a good meaty problem. Okay, so what do we do? Multiply 2 times 117. That just takes us back to the 234. And we need a factor table for 234. This is a good time to talk about your calculators. Folks, on your calculator, obviously you can just start taking 234 and dividing it by counting numbers. So, it's time consuming, but you can do it. 234 divided by 1, 234 divided by 2, 234 divided by 3, and that's how you make a factor table. You just start dividing. So let's see, it was 1 and 234, 2 and 117, 3 and 78. There's now 234 divided by 4, no. 234 divided by 5, no. 234 divided by 6, ooh, 6.
That one.
Is it that one?
Yeah.
How do you know? How do you know, Jesus? Oh, because it was a negative 234 and you're looking for differences that make 33? Okay, you got me there. That is the one, so I guess we can stop. So we want a positive 33. Which is positive and which is negative? Yeah, 6 is negative, 39 is positive. All right, let's rewrite that middle term. 2x squared minus 6x plus 39x minus 117 equals 0. And now we already have a plus in between our two groups. So what can we factor out of the first one? 2x. So that's 2x outside of x minus 3. Does 39 divide out of 117?
Yep.
It sure does. In fact, it's still sitting there looking at me in the factor table. 39, oh, there it is. 39 does divide into 1, oh, well, 39 goes into 234. So, 39 does go into 117, though. So you just have to check your calculator. Sid, what is it?
3.
3. Oh, good. I'm glad it was 3. Right? Didn't it have to be 3? It was going to have to be. Of course, you'd still want to check. But it is x minus 3. So we have x minus 3 and 2x plus 39 equals 0. Yes, Jesse?
You're gonna give us a lot of space to do this.
I sure didn't. Yeah, that's not a ton of room right there. I should have made it much bigger. Oh, I'll give you more space on the test.
Yeah.
Yeah, I'll give you a
That's what I meant more.
Oh, okay. I thought you were just saying my mistake and not making enough room now. I was acknowledging it, yes. But yeah, on the test, I'll give you full page. Now you can make a really nice picture, show all your calculations. Yeah, sorry about that. Okay, so folks, after all that work, we finally get to do our lesson for the day, which is the zero product rule. We're now ready to do the zero product rule. Either I can make x minus 3 equal to 0, or I can make 2x plus 39 equal to 0. And therefore, x is 3, or x equals negative 39 halves. Which is what? Negative 19 and a half? Now, provided we've done everything correctly and we haven't made any mistakes at all, what would happen if I plug 3 into this equation? It'll be true, right? It'll be true. What will happen if I plug negative 19.5 into this equation? It'll be true. Yeah, both of these solutions that we just came up with are mathematically true. Both of those will make the equation that we made true. But which one makes sense in the context of a word problem where we're talking about the width of a gravel path? Just 3. 3 is the only one that makes sense. I mean, first of all, because a gravel path can't be negative feet wide. But second of all, could our gravel path really be 19 and a half feet wide? I mean, look at how wide the garden is. 20. Would you really make a gravel path around the garden that's almost as wide as the garden itself? That would be a really weird parking lot of a garden. It'd be wild. So for those two reasons, 19 and a half is called what solution? Extraneous. Extraneous. Mathematically true, but nonsense. Isn't extraneous a good word? Do we ever use the word extraneous in English?
Sometimes.
Do you really?
Yeah, and you can use it instead of irrelevant.
Oh, that's funny. That's true. Irrelevant. That's another good one. I like that word irrelevant. I was about to say extraneous. That could be like the new insult you use on someone this week. Not that any of you would ever insult anyone or be mean to anyone, but if you had to, you'd be like, man, you're being so extraneous, or look at who are you, extraneous, or I don't know. Maybe don't actually say that, but ooh, irrelevant. That would really cut to the quick. Man, you're irrelevant. Ooh, that'd be painful. Okay, so that's extraneous. It's 3 feet wide. Did we do it right? What's step 4? We just solved for x. That's all we did. We just solved for x. Verify the truth. So is the gravel path really 3 feet wide? To do so, you have to draw another diagram. And we're actually going to check. So if the original was 20 by 13, and now the gravel path is 3, then how wide is the overall garden? 26. And then how tall is the original garden, or how tall is the overall shape? Yeah, 13 plus 3 plus 3, that's 19. And is 19 times 26, does that equal the area of the whole thing? Is 19 by 26 equal to 494? Yes. Oh, goody. That's the end of the problem. I swear that's the end.
It's like 10.
I'm surprised only 10. Problem like that could take much longer than 10 minutes. Yeah, so folks, we did it. That problem was epic. It is an epic problem. It is definitely on your test. The good news is, I gave you another one right now to practice. It's about Doris and her fish pond. So it's the same setup. So you have another one now, and we're going to immediately practice it again. Because just doing it once, you can finish a long, lengthy math problem and still feel confused. Because we just barely made it. We just finished. Now let's try the whole thing again. And you've got the whole thing there to look at, to check and verify your work. What do we want to begin by doing? Draw a really good picture. Draw a really good picture. The quality of the picture will determine your success. So let's see. Doris has a rectangular fish pond that is 6 by 9. She wants to put a grass in a strip of uniform width around the pond. She has enough grass seed for 126 square feet. How wide will the strip be? Is this the same problem? Yeah. It's different numbers and it's Doris, but it's still the same problem. Well, nice, folks. You can chat with each other, share work, collaborate. Bust out a ruler. Pick out your crayons.
Thank you.
Yeah.
Actually, it's 2-3.
You have to go. Okay. Hey, you can watch the rest of it.
Okay.
Hey, looking good, Jackie. This looks great. Like X is around, like great down there. Great formula. I like the creative method. That's fun. Very nice. Yep, great setup. Looking good, Ingrid.
Trying to figure out how can I,
Yeah, we do want to set up an equation. So you notice how we have the inner rectangle, and you already have that. Your inner rectangle has an area. Is that A?
Yeah.
What is it? What letter
How
is
is
that?
this better next time? This one's better.
Yeah, well, that would also
Oh,
be
sorry.
A, because that's your area.
Yeah.
Yeah. Yeah, all of those are actually A. Area equals length times width, so it's 6 times 9, which is, yeah, there you go. So the inner rectangle didn't do anything for us, but the outer rectangle did. We need to know the dimensions of the outer rectangle. So how wide is the outer rectangle?
X.
Well, it's at least 9
9.
wide, and then plus another X right there, and another X over there. So how wide is it total?
X plus 9 plus X.
There you go, X plus 9 plus X, yeah. Good, I like how you're doing that, just writing it there along the bottom. Now combine like terms. 1x plus 1x is,
X squared. No.
1 apple plus 1 apple is,
X plus.
x is an object. 1x, put a 1 in front of it, plus 1x. So if I have 1 apple plus 1 apple, I have,
2 apples.
so 1x plus 1x is
2.
2x. Yeah, so it's 2x plus 9. Very good, put it in parentheses. That is your length. Now do the width.
So E X
Mhm.
plus 6
Mhm.
plus X.
There you go. Yeah, very good. And then you can combine like terms again. Well, let's not start building the formula yet. Let's just finish labeling your diagram. Go ahead and simplify that just like you did that one.
Mhm.
What's x plus 6 plus x?
2x plus 6.
There you go, write it there and put it in parentheses. Okay, now you know the dimensions of the
Okay.
outer rectangle. Okay, that's what you're looking for, the outer rectangle. Now, furthermore, that since that's the dimension of the outer rectangle, you need to know the area of the whole rectangle. The inner area is what?
54.
And the outer area is,
126.
so what's the total area?
It'd just be 54 plus 126.
Yeah. Yep, you're just adding them together. I'll be right there, Kristen.
180.
There you go. Now you're ready for an equation. And I would write down length times width equals area. And then below those, put in that information.
Okay.
Yeah, because maybe I didn't do that first time. But that's what we want to have. So,
Okay.
Yeah, label it like that because then you can put in your 2x plus 9, your 2x plus 6, and then your 180.
Okay.
Crystal.
See what you mean about this stuff.
So that changed kind of everything. But it did, now you're on your right track. Yeah, so length times width equals area. And here's just my recommendation. Is that working? Yeah. I would write the formula as big as you are going to do it. So spread it out. That way you're mapping up each part with what it is.
Okay.
It makes it easier to see.
It does.
Yeah, much better.
Would it be?
Yep, that's 180. So now you begin the process of foiling. Yeah, really nice. How's it going? Yeah, nice. Oh, very nice, because now you're ready to factor. Oh, how exciting. It doesn't come back, right? That was the next one. But it was the process.
Well, folks, I don't want to interrupt any of you because you're all working along so nicely, but just to verify your numbers so that we all know that we're working with the same numbers, what was my total length? The total length? Yeah, 2x plus 9. And then my total width? 2x plus 6. And my total area? 180. So this is our initial equation that we set up. And then you do FOIL. So let's just check your FOIL numbers. So that'd be 4x squared plus 12x plus 18x plus 54 equals 180.
Right.
And then you combine your like terms and you have 4x squared plus 30x. And then if I go ahead and move my 180 over right now, I have negative 126. So everybody make sure, before you get too much farther, that you had 4x squared plus 30x minus 126. Is that correct?
Yes.
Okay. So can you factor out a 4? No. You can factor out a 2, though. So now you'll all be working on factoring 2x squared plus 15x minus 63. Because we're all just going to divide that 2 off so that you don't have to deal with the 2 anymore. So we'll all work on factoring 2x squared plus 15x minus 63.
Did it work? Did you see what it is? Just that one number. Oh, I got it. So what is the area of this one? 6 by 9.
The 180. The area for both.
So then the combined total area is 54.116. Yeah, there you go. So that's what this is. Now, where did this formula come from? Yeah, and its area equals 6 minus 10.
Oh.
No, you got it.
Yeah.
2.
Aren't you supposed to talk?
It's a new school numbers, right?
I thought so.
When you
I didn't get addition for the little one, so please. Oh, the 63 and the Let's go. I was like, why am I not getting it?
Your turn. find the factors for 126. Oh, right, because 2 times 63 is 1. Oh, yeah, that is, oh my gosh. So yeah, instead of 2 times 1. But hey, that was such good practice. That's the factor that we're going to do. So.
What's going to be? Stuck. Oh, it looks like you finished.
Yeah, but I was trying to figure out how to.
Put that in there.
Yeah.
Well, you see how your little arrows right there for that's X? So then you can put another one up here, that's X. Yeah, just a little width is 3. Just a little width is 3. That's not 3, that's 6. Oh, wait.
Yeah.
Where's it? Oh, okay.
I kind of like in my mind. I know this is
Now,
3. I'm just trying to figure out.
oh, gotcha.
why it's too wet.
Right. So first of all, you have this 9 and 6 in there. I would not have it in like that because this side is shorter. This side is longer. So what should be 9? Yeah. We just want our drawing to always be as accurate as possible, as realistic as possible. So there we go. So if it's already 9, and then you tack on 3 more here, 3 more there.
Oh, why that?
Yeah.
Oh,
Yeah.
so I was like that.
Yeah, that's what you did. Hey, very nice. Yep. So now you have this equal to 0.
And then I started going.
Oh, yeah, very good. Yeah, this is it, Ingrid. So then you did 2 times 63. You have to do 2 times 63.
Oh,
You're not doing the
okay,
factor
got
table
it.
for 63. You have to multiply it. Yeah, really good. Well, nice. You're writing in your final formula. That's great. I don't know what I got. 43 47. If you look at 42 over, it's 42 divided by 3. I mean, it's an extraneous solution. We're not going to use it anyway, but this will be accurate about it. You guys optimistically looking at the next one? Give it a shot. See if you can just make a picture of what they're talking about. Yeah, I know. That's the tricky part. It's coming up with that. Ah, makes it fun. Well, yeah. You can do that. 63, 126. You're looking for 2 numbers. The difference is 15. Yeah, it's close. Yeah, it's close. Yeah, because it's going to be plus 15. So it's going to be plus 1 over minus 6. That's correct.
All right, folks, let's compare our factoring work. So in order to factor this with the non-basic factoring technique, we have to multiply the 2 times the 63, which is negative 126. Well, I don't have a factor table for that, but 1 and 126, 2 and 63, 3 and 42, 4 and nothing, 5 and nothing, 6, yeah, 6 and 21. And that's as far as we have to go, right? Because we want numbers whose difference is 15. And so that's 6 and 21. Which is positive, which is negative?
Negative.
Yeah, negative 6, positive 21. So now we can rewrite and get 2x squared minus 6x plus 21x minus 63. And then we factor by grouping. And what can we take out of the first binomial? 2 and 2x. So that's x minus 3. And then what can we take out of the second binomial? Yeah, actual 21. And that's x minus 3. And so one of our binomials is x minus 3. And the other binomial is 2x plus 21. And so we set both of those equal to 0. This is where we actually bring in the zero product rule. Something times something equals 0. That tells us that either x minus 3 is equal to 0, which means x equals 3, or 2x plus 21 is equal to 0, which means x is equal to negative 21 halves. Walking around the room, I think I saw most of you have x equals 3, but then I saw lots of different fractions. Like not just negative 21 halves. So I'm just curious for you to look at your own work. If you did get 3, but you didn't get negative 21 halves, I'm curious how that happened. I don't know. It's just a mystery that I throw back out to you. All right, so in any case, what's the answer? 3. Yeah, because a gravel path, sorry, this is not a gravel path. This is a grass path around the fish pond, cannot be negative 10.5 feet wide. Plus, could 10.5 really be the answer? That would be really wide. I mean, how wide is the fish pond? 9. Would she build a path that's 10 feet wide around the whole thing? I mean, that's just weird architecture. I don't think any feng shui would ever make the path twice as wide as the object itself. I don't know, that's just me. So our path is 3 feet wide. Now let's verify the truth. If we have a fish pond that's 6 by 9, how wide is the total? Since you've got an extra 3-foot kicker on either side, it's 9 plus 3 plus 3, which is 15. And then 6 plus 3 plus 3, 12. And so is 15 times 12 equal to 180? That was the total area we said. Yeah, 15 times 12 is equal to 180. So folks, I hesitate to share with you a shortcut. No, there's no square root. And now again, I hesitate. Why do I hesitate? Because what I'm about to show you, you cannot use on the test for credit. All right, if you do this on the test, no credit. All right, but let's just think. We started the problem with what information? Yeah, you know, wait, what?
There's no point showing us, we can't use it.
I think there's a lot of point because it's interesting and it's
It's gonna get us
cool.
pissed
And you
if we
can,
can't use it.
what Genesis?
It's gonna get us pissed because we can't use it.
You can use it to check your work. You can use it to check to make sure you have the right answer. Wouldn't that be nice? Okay, so what did they tell us? It was 6 by 9, and then that area there is 54 then. And what was the area of the gravel path? 126. So the total area was what? 180, right? Our total area is 180? Okay. Now the dimensions, all right? The dimensions, how much longer is the width than the, I'm sorry, how much longer is the length than the width? 3? And if I add 2x to both sides, how much longer is the length than the width now? Still 3. This is still 3 feet longer than this. It started out 3 feet longer, it's still 3 feet longer. So what am I looking for? I'm looking for two numbers that multiply to equal 180 that are how many units apart? 3. I'm looking for two numbers that multiply to equal 180 that are 3 units apart. So 180 is 1 times 180, 2 times 90, 3 times 60, 4 times 45, 5 times what? I don't even know. 24, Genesis, I can't say it. Please, you said you'd be pissed. 5 times 24, 6 times 30, 7, 8, 9 times 20. Are we done? 10 times 18. Oh no, there's more. After 10, 11, 12 times 15. Okay, there's our factor table. Which one is 3 units apart? 12 and 15. And what's the dimensions of the total thing? 12 and 15. And from that, could you figure out what x was? Like if I told you that the overall is 12 by 15, and I told you this was 6 by 9, then could you figure out how wide that would have to be such that x, or 6 plus x equals 12?
Yeah.
Sure you could. 6 plus 2x equals 12. Now you can just look at that and say, well, hey, I subtract a 6 and I have 2x equals 6 and x equals 3. It's just a different way of approaching the problem. I shared it with you, Sydney Genesis, for entertainment value. Wasn't that impressive? Wasn't that delightful? Wasn't that amazing? But yeah, you got to show the full solution to get credit on the test.
Yeah.
I actually like that one.
Oh, you do like this one better? Okay, well that's fine because that's what that's the skill we're learning anyway. Okay, really nice, folks. Folks, these problems were challenging, weren't they? I thought so. I think theirs were really good. Folks, I never leave class early because you paid to be here, and I'm here to be your support. But on the other hand, we just finished a really massive problem, and I don't want to do another different problem because I want to let that sink in so you all go home and dream about it tonight. So for the next 4 minutes, I'm making myself available to you to answer any questions you have. I am not dismissing you early. If you leave, I can't stop you. but I am making myself available to you to answer any questions you have. Thank you, folks. You worked really hard today. Great effort. Yeah.